When you close your eyes and picture the sun, what color do you see? Most likely, you imagine a circle of brilliant yellow, perhaps with rays extending outward, warming everything it touches. This is the sun we know, the sun we've drawn since childhood, the sun that appears in paintings and photographs and memories of summer afternoons. It is yellow, or perhaps sometimes orange, especially as it settles toward the horizon at the end of a long day. This seems like an obvious truth, as certain as the fact that the sky above us is blue, as reliable as the rhythm of sunrise and sunset. And yet, there is something quietly remarkable waiting to be understood. Something that asks us to reconsider what we think we know about the star that gives us light and warmth. The sun, that familiar yellow disk in our sky, is not actually yellow at all. When viewed from beyond Earth's protective blanket of atmosphere, when observed in the absolute emptiness of space where there is nothing to alter or interrupt its light, the sun appears white. Purely, completely white. This is not a philosophical claim or a matter of perception or interpretation. It is a measured, verified scientific fact, confirmed by instruments in space, by astronauts aboard the International Space Station, by satellites that observe the sun without the interference of air. The sun emits light across all the wavelengths that our eyes can detect. When all these colors combine together in equal measure, the result is white light. The sun is white. So why then, when we look up at midday, does it appear yellow? Why do we see golden light streaming through windows? Why does every child instinctively reach for a yellow crayon when asked to draw the sun? The answer lies not in the sun itself, but in the journey its light must make to reach us. Between the sun and our eyes stretches an ocean of air, kilometers upon kilometers of atmosphere, filled with molecules that interact with sunlight in specific, measurable ways. These interactions change what we see, filtering and scattering the sun's light, removing certain wavelengths while allowing others to pass through. This is a story about light and atmosphere, about wavelengths and molecules, about the physics that shapes our everyday experience of the world. It is a story that connects the innermost workings of atoms to the grandest scales of space, that links the chemistry of Earth's air to the nuclear fusion happening in the sun's core. It is a story that has taken humanity centuries to fully understand, requiring careful observation, mathematical insight, and the ability to send instruments beyond our planet's boundaries. We will move slowly through this explanation, taking time to understand each piece before moving to the next. There is no hurry. The sun has been white for 4.5 billion years. Its light has been traveling through Earth's atmosphere for just as long. This phenomenon has existed since long before human eyes, evolved to perceive it, and it will continue long after we are gone. We can take our time to understand it properly. We will begin with light itself, examining what it is and how it behaves. We will explore the sun as a source of this light, understanding why it produces the spectrum that it does. We will look at Earth's atmosphere in detail, understanding what it is made of and why that matters. We will trace the path of sunlight as it enters the atmosphere, watching what happens to different wavelengths as they encounter molecules of nitrogen and oxygen. We will see how this changes at different times of day as the sun moves from overhead to the horizon. And we will understand how our own eyes and brains interpret the light that finally reaches us, creating the experience of color that feels so immediate and real. By the end, you will understand not just that the sun is white, but why we see it as yellow. You will understand the invisible interactions happening in the air above you every moment of every day. You will see the familiar sky with new awareness, recognizing the physics at work in something as simple as afternoon sunlight. Let us begin with the most fundamental question of all. What exactly is light? Light is perhaps the most familiar thing in our daily experience, and yet it operates in ways that can seem almost magical when examined closely. We flip a switch and a room is illuminated. We step outside and the world is visible. We see colors, shapes, distances, textures. All of this is made possible by light, by electromagnetic radiation in a narrow band of wavelengths that our eyes happen to be able to detect. But light is far more than just what we can see. The visible spectrum, the rainbow of colors from red to violet, is only a tiny sliver of a much larger electromagnetic spectrum. This spectrum extends in both directions far beyond what human eyes can perceive. At one end are radio waves, with wavelengths measured in meters or even kilometers. These waves are so long that they can pass through walls and travel vast distances, carrying information that radios and televisions decode into sound and images. Moving along the spectrum toward shorter wavelengths, we encounter microwaves, which are used in communication and, famously, in heating food. Then comes infrared radiation, which we experience as heat. Anything warm emits infrared light, including our own bodies, though we cannot see this with our eyes. Then, in a narrow band between approximately 400 nanometers and 700 nanometers in wavelength, we find visible light. A nanometer is 1/1000th of a meter, almost impossibly small. To put this in perspective, if you could line up individual atoms side by side, it would take several atoms to span just 1 nanometer. The wavelengths of visible light are measured in hundreds of these nanometers. This is the light that our eyes evolved to detect, likely because the sun emits strongly in this range and because these wavelengths can penetrate Earth's atmosphere and ocean water reasonably well. Beyond violet, at wavelengths shorter than 400 nanometers, we find ultraviolet light. This is the radiation that causes sunburns, that Earth's ozone layer helpfully absorbs before it can reach the surface in full strength. Shorter still are X-rays, which can pass through soft tissue but are blocked by bone, making them useful for medical imaging. At the extreme short end of the spectrum are gamma rays, produced by radioactive decay and by the most energetic events in the universe. All of these, from the longest radio waves to the shortest gamma rays, are fundamentally the same phenomenon. They are all electromagnetic waves, oscillations in electric and magnetic fields that propagate through space at the speed of light, which is approximately 300,000 kilometers per second in vacuum. The only difference between them is their wavelength, or equivalently, their frequency. Wavelength and frequency are inversely related. Long wavelengths mean low frequencies, many meters between wave crests and relatively few oscillations per second. Short wavelengths mean high frequencies, tiny distances between crests, and many trillions of oscillations per second. The visible spectrum spans from red light at around 700 nanometers down to violet light at around 400 nanometers. Red light has the longest wavelength we can see and therefore the lowest frequency in the visible range. As we move through the rainbow toward violet, wavelengths get progressively shorter and frequencies get higher. Orange light has a wavelength around 600 nanometers. Yellow sits around 580 nanometers. Green is near 520 nanometers. Blue is around 470 nanometers. Violet approaches 400 nanometers. These precise numbers matter because, as we will see, how light interacts with matter depends critically on wavelength. The same physical interaction can affect blue light very differently from red light simply because their wavelengths differ. This wavelength dependence is the key to understanding why the sun appears yellow despite being white. Now, when we say that light is white, what does that actually mean? White is not a single wavelength. There is no such thing as white light in the same way there is red light at 700 nanometers or blue light at 470 nanometers. Instead, white light is a mixture. It contains all the visible wavelengths in certain proportions. When all the colors of the rainbow are present together, our eyes and brain interpret this as white. This can be demonstrated in several ways. The most famous is the prism experiment that Isaac Newton performed in the 1600s. Newton allowed a beam of sunlight to enter a darkened room through a small hole. He then placed a glass prism in the beam's path. As the light passed through the prism, it bent, an effect known as refraction. But different wavelengths bent by different amounts. Red light bent the least, violet light bent the most, and the other colors spread out in between. The single beam of white sunlight separated into a spectrum of colors, a rainbow arranged by wavelength. This showed that white sunlight contains all these colors. They are normally mixed together, traveling in the same direction, and our eyes perceive this mixture as white. But the prism reveals the components, demonstrating that white light is actually composed of many wavelengths. The same principle is at work when you see a rainbow in the sky after rain. Water droplets in the air act like countless tiny prisms. Sunlight enters these droplets, reflects off the back surface, and exits at an angle that depends on wavelength. Red light exits at a slightly different angle than violet light. When conditions are right, with the sun behind you and rain in front of you, these separated colors become visible as concentric arcs across the sky, with red on the outside and violet on the inside. The rainbow shows you that sunlight contains all these colors, usually mixed together invisibly. For light to appear white, it must contain a fairly even distribution of all visible wavelengths. If one color dominates strongly, we would perceive the light as having that color. If red is much stronger than other colors, the light appears reddish. If blue dominates, the light appears bluish. True white light requires balance across the spectrum. The sun, as we will explore in detail next, produces such a balanced spectrum. Its light, when measured in space before entering Earth's atmosphere, contains all visible wavelengths in proportions that our eyes interpret as white. This is not a coincidence or an accident of nature. It is a direct consequence of the sun's surface temperature and the physics of thermal radiation. The sun glows because it is hot, approximately 5,778 Kelvin at its visible surface, and objects at this temperature emit light with a very specific spectrum that happens to peak in the middle of the visible range and spread across all the colors we can see. Understanding this requires understanding blackbody radiation, a concept that emerged from physics in the late 1800s and early 1900s. It is worth taking time to grasp this concept because it explains not just why the sun is white, but why hotter stars are blue and cooler stars are red, and why anything warm enough will glow with visible light. But before we go there, it is worth pausing to appreciate how remarkable it is that we can know these things at all. We cannot travel to the sun's surface. We cannot hold a piece of star in our hands. We cannot even look directly at the sun without damaging our eyes. And yet, by studying light, by measuring its properties carefully, by understanding the physics of how hot objects radiate energy, we can determine the sun's temperature to within a few degrees. We can know its composition, its age, the nuclear reactions happening in its core. All of this from analyzing the light that reaches us across 150 million kilometers of space. This is the power of light as a messenger. It carries information encoded in wavelength, intensity, polarization. By learning to read this message, we can understand the universe in ways that would have seemed impossible to earlier generations. The story we are telling now about why the sun appears yellow is just one small example of what can be learned by paying careful attention to light. To understand why the sun emits white light, we must understand what the sun is and how it produces light. The sun is a star, an enormous ball of plasma held together by its own gravity, with nuclear fusion reactions in its core converting hydrogen into helium and releasing tremendous amounts of energy in the process. This energy makes its way from the core to the surface over hundreds of thousands of years, transported first by radiation and then by convection, until it finally emerges as light from the visible surface called the photosphere. The photosphere is the layer we see when we look at the sun. It is not a solid surface because the sun has no solid parts. It is simply the layer where the gas becomes transparent enough that photons can escape into space. Below this layer, the sun is opaque, with photons constantly being absorbed and re-emitted by atoms and ions. Above this layer, the gas is too thin to emit much light. The photosphere itself is where the transition occurs, where light can finally break free. This layer has a temperature of approximately 5,778 Kelvin. This is the effective temperature, the temperature that determines what kind of light the sun emits. To understand what this means, we need to understand the concept of blackbody radiation. A blackbody is an idealized object that absorbs all light that falls on it and emits light purely based on its temperature. Despite the name, a blackbody does not necessarily appear black. In fact, anything warm enough emits visible light and will glow. A black body is called black only because it does not reflect any light. All the light it emits comes from its own thermal energy. Real objects are not perfect black bodies, but many objects approximate black body behavior quite well. The Sun is an excellent approximation to a black body. Its surface emits light according to its temperature, following well-understood physical laws. The first important law is the Stefan-Boltzmann law, which tells us that the total energy radiated by a black body increases dramatically with temperature. Specifically, the energy radiated per unit area is proportional to the fourth power of temperature. If you double the temperature, the object radiates 16 times as much energy. This is why hot objects glow so brightly. The second important law is Wien's displacement law, which tells us that the wavelength at which an object emits most strongly depends on its temperature. Hot objects peak at short wavelengths, cool objects peak at long wavelengths. There is a precise mathematical relationship. The peak wavelength in nanometers equals approximately 2,900,000 divided by the temperature in Kelvin. For the Sun, with a temperature of 5,778 Kelvin, this gives a peak wavelength of approximately 502 nanometers. This is in the green-blue part of the visible spectrum, so in one sense, the Sun peaks in the green. However, this does not mean the Sun appears green. This is a common source of confusion, so it is worth being very careful here. When we say the Sun's spectrum peaks at 502 nanometers, we mean that if you plot the intensity of light at each wavelength, the curve reaches its maximum near this wavelength. But the curve is broad, extending far on either side of the peak. The Sun emits strongly at 400 nanometers, at 500 nanometers, at 600 nanometers, at 700 nanometers. It emits across the entire visible spectrum, plus far into the infrared and somewhat into the ultraviolet. Moreover, the perception of color depends on how all the wavelengths combine, not just on where the peak occurs. A narrow beam of light at exactly 502 nanometers would indeed appear greenish. But the Sun's broad spectrum, containing all colors in substantial amounts, does not appear green. When all these wavelengths combine, our visual system interprets the result as white. This is actually slightly fortunate. If the Sun were much hotter or much cooler, its light would not appear white. A very hot star with a surface temperature of perhaps 20,000 Kelvin would peak in the ultraviolet. Even though it would still emit visible light, it would emit more blue than red, and its light would appear bluish-white. These are the blue giant stars we see in the night sky, stars far more massive and hotter than our Sun. Conversely, a cooler star with a temperature of 3,000 Kelvin would peak in the infrared. Such stars still emit visible light, but they emit more red than blue, and they appear reddish. These are red dwarf stars, smaller and cooler than the Sun, the most common type of star in the galaxy. The Sun, with its temperature of 5,778 Kelvin, sits in a sweet spot where its emission spectrum is balanced across the visible range. It emits roughly similar amounts of red, green, and blue light. When all these wavelengths combine, the result is perceived as white by human eyes. This can be quantified precisely using something called the CIE color space, a mathematical system developed by the International Commission on Illumination to describe how human color vision works. In this system, colors are mapped to specific coordinates. Pure white light containing equal energy at all visible wavelengths corresponds to coordinates of approximately 0.3, 0.3. When scientists measure the Sun's light in space and calculate its CIE coordinates, they get values very close to this. The Sun is, objectively, white. It is worth emphasizing that this is not a matter of opinion or definition. The Sun's spectrum can be measured with instruments. Its color can be calculated from that spectrum. The calculation uses the known response curves of human cone cells, the light-sensitive cells in our retinas that enable color vision. The result is unambiguous. The Sun emits white light. This white light is what leaves the Sun's surface and travels through the vacuum of space toward Earth. For most of this journey, nothing happens to alter it. Space is empty. There are no molecules to absorb or scatter the light. The electromagnetic waves simply propagate outward from the sun in all directions at the speed of light, crossing the 150 million kilometers to Earth in about 8 minutes and 20 seconds. Astronauts aboard the International Space Station, orbiting just a few hundred kilometers above Earth's surface, but above the vast majority of the atmosphere, can look at the sun through appropriate filters and confirm that it appears white. Satellites and space telescopes observe the sun in many different wavelengths and measure its spectrum directly. These measurements confirm the theoretical predictions. The sun's light, measured in space, is white. But we do not live in space. We live at the bottom of an ocean of air, and as sunlight passes through this atmosphere, its journey becomes far more complicated. The light that began as pure white at the sun's surface arrives at our eyes altered by its passage through the atmosphere. To understand how and why this happens, we must understand what Earth's atmosphere is made of and how these components interact with light. Before we descend into the complexities of atmospheric physics, it is worth pausing to fully appreciate the white truth. The sun is white. This is not just a theoretical calculation or a prediction based on temperature. It is an observable fact, confirmed by every measurement made from beyond Earth's atmosphere. When astronauts first traveled into space in the 1960s, they took with them cameras and the ability to observe the sun directly, though through proper filters to protect their vision. What they saw was not the familiar yellow disk of Earthbound observations, but something subtly different. The sun appeared brighter, certainly, without the atmosphere to dim it. But more significantly, it appeared whiter, without the yellowish tint that characterizes its appearance from the ground. This was not a surprising observation to scientists, who had already calculated from theory what the sun's color should be. But it was confirmation. Nonetheless, the sun, viewed from space, is white. The International Space Station, which has been continuously occupied since the year 2000, orbits at an altitude of approximately 400 kilometers. At this height, it is above 99% of Earth's atmosphere by mass. The tiny amount of air that remains at this altitude is so thin that it has essentially no effect on sunlight. For practical purposes, the space station exists in the vacuum of space, and observations of the sun from the station are observations of the sun's true color. Astronauts have described the sun's appearance from this vantage point many times. Without atmospheric filtering, the sun's light is intensely bright and appears pure white. The light streaming through the station's windows is white light, not the golden light we experience on Earth. When this light illuminates the interior of the station, it reveals colors as they truly are, without the yellow cast that characterizes earthly illumination. The difference is subtle but real. Our brains are remarkably good at compensating for the color of illumination, a phenomenon called color constancy. A white sheet of paper appears white whether we view it under sunlight, moonlight, or indoor lighting, even though these light sources have quite different spectral compositions. Our visual system adjusts, factoring out the color of the light source to determine the inherent color of objects. This is useful for survival, allowing us to recognize objects regardless of lighting conditions, but it also means we do not always consciously notice when the illumination is yellowish or bluish or neutral. Nevertheless, when astronauts return from space and experience Earth-normal sunlight again, many report noticing the difference. The light seems warmer, more golden, less brilliant. This is what we have adapted to, the light filtered by atmosphere, but it is not the sun's true color. Scientists have measured the sun's spectrum from space with great precision. Satellites like the Solar Dynamics Observatory continuously monitor the sun in many different wavelengths, from the ultraviolet through the visible and into the infrared. Instruments on these satellites measure how much light the sun emits at each wavelength with exquisite accuracy. When these measurements are plotted on a graph, they show a smooth curve that extends across the entire visible spectrum. The curve is not perfectly flat. It has some structure, with certain wavelengths slightly stronger or weaker due to absorption by specific elements in the sun's atmosphere. These absorption lines are actually incredibly useful. They allow scientists to determine what elements are present in the sun and in what amounts. By analyzing which wavelengths are absorbed, we can create a detailed chemical census of the sun's outer layers. This is how we know the sun is primarily hydrogen and helium, with small amounts of heavier elements like oxygen, carbon, iron, and many others. But setting aside these fine details, the overall shape of the spectrum is a broad curve that covers all visible wavelengths substantially. There is no single color that dominates. Red light, green light, blue light, all are present in significant quantities. When all these wavelengths combine in the proportions that the sun actually emits them, the result is white light. This can be calculated precisely. Scientists take the measured spectrum, multiply it by the response curves of human cone cells, which show how sensitive each type of cone is to each wavelength, and integrate to find what signals would be sent to the brain. The result can then be plotted in the CIE color space, showing exactly where this light would appear in terms of human color perception. For sunlight measured in space, this calculation yields coordinates very close to pure white. The sun is white, not yellow, not orange, not any single color. White, a balanced mixture of all visible colors. This fact has been known for decades now, confirmed by countless measurements from space. And yet, the sun appears yellow to us on the ground. This is not an illusion or a mistake in our perception. When we look at the sun, we are seeing it through Earth's atmosphere, and the atmosphere changes the light. The light that leaves the sun's surface as white arrives at our eyes as something yellower. To understand why requires understanding air itself, what it is made of, and how it interacts with light on the molecular level. The atmosphere that surrounds our planet is a relatively thin layer of gas held to Earth's surface by gravity. It extends upward for hundreds of kilometers, gradually thinning with altitude until it merges almost imperceptibly with the vacuum of space. But the vast majority of the atmosphere's mass is concentrated in the lowest few kilometers, in the layer we call the troposphere, where weather occurs and where we live and breathe. At sea level, air has a pressure of approximately 101,325 pascals, or 1.013 bar, or 1 atmosphere by definition. This pressure is the weight of all the air above pressing down on each square meter of surface. As you ascend a mountain or ride in an airplane, the pressure decreases because there is less air above you. By the time you reach the cruising altitude of a commercial airliner, around 12,000 meters, the pressure has dropped to less than a quarter of its sea level value. At the altitude of the International Space Station, 400 kilometers up, the pressure is less than 1/1,000,000th of sea level pressure. For practical purposes, there is no air there at all. But what exactly is air? What is this invisible substance we breathe and move through every moment of our lives? Air is a mixture of gases, primarily nitrogen and oxygen, with small amounts of other substances. The exact composition can vary slightly, depending on location and time, especially for components like water vapor, which change with weather. But the major components are remarkably stable. If we consider dry air, removing the variable water vapor content, the composition is approximately 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.04% carbon dioxide, and trace amounts of other gases including neon, helium, methane, krypton, and hydrogen. These percentages are by mole fraction, meaning by the number of molecules. 78 out of every 100 molecules in dry air are nitrogen molecules. 21 are oxygen molecules. About 1 is an argon atom. The remaining tiny fraction includes everything else. Nitrogen molecules consist of 2 nitrogen atoms bound tightly together. The chemical formula is N2. These molecules are very stable, not reacting easily with other substances under normal conditions. Nitrogen is an inert gas for most practical purposes, which is why it makes up such a large fraction of the air without causing us problems. If air were mostly oxygen, fires would burn uncontrollably. If it were mostly carbon dioxide, we could not breathe it. Nitrogen provides a neutral background, diluting the reactive oxygen to safe levels. Oxygen molecules also consist of 2 atoms, O2. Unlike nitrogen, oxygen is highly reactive. It is essential for cellular respiration in animals, the process by which our cells extract energy from food. It is also necessary for combustion, enabling fires to burn. The oxygen content of air, 21%, is high enough to support complex life, but low enough to prevent runaway oxidation reactions. Argon is a noble gas, completely unreactive. It exists as individual atoms rather than molecules. It is present in air simply because it was released from rocks over geological time as radioactive potassium decayed. It does nothing of biological or chemical importance, but it makes up almost 1% of the atmosphere. Carbon dioxide, at 0.04% or about 400 parts per million, is a tiny fraction of air but plays an outsized role in Earth's climate. It is a greenhouse gas, absorbing infrared radiation and helping to keep the planet warm. Plants also require carbon dioxide for photosynthesis. In recent decades, human activities have increased the carbon dioxide concentration, raising concerns about climate change, but it remains a trace component of the atmosphere. The other gases are present in even smaller amounts, often measured in parts per million or parts per billion. They include neon at 18 parts per million, helium at 5 parts per million, methane at just under 2 parts per million, and many others. These trace gases can be important for specific processes, but they make up an almost negligible fraction of the total. Water vapor content varies widely, from nearly zero in desert air to as much as 4 or 5% in hot, humid tropical air. Water vapor is critical for weather and climate as it transports heat and forms clouds and precipitation. But for understanding how air affects sunlight, we can mostly set aside water vapor and focus on the major dry components, nitrogen and oxygen. What matters for our story is not just what air is made of, but the size of these molecules. A nitrogen molecule is approximately 3.7 angstroms across, where 1 angstrom is 1/10 of a nanometer. An oxygen molecule is slightly smaller, about 3.5 angstroms. These are incredibly tiny, measured in units that represent roughly the spacing between atoms in a crystal. To put this in perspective, remember that visible light has wavelengths from 400 to 700 nanometers. That means the wavelength of visible light is more than 100 times larger than the size of a nitrogen or oxygen molecule. Blue light, at 470 nanometers wavelength, has a wavelength about 127 times larger than a nitrogen molecule. Red light, at 700 nanometers, has a wavelength about 189 times larger than a nitrogen molecule. This size relationship is crucial. When light encounters a particle, how it interacts depends on the ratio of the particle size to the wavelength. If the particle is much larger than the wavelength, geometric optics applies, and we can think of light as rays bouncing off surfaces. If the particle is roughly the same size as the wavelength, complex interference effects occur, described by my theory. But when the particle is much smaller than the wavelength, as is the case for air molecules and visible light, a different type of interaction occurs called Rayleigh scattering. Rayleigh scattering, named after the British physicist Lord Rayleigh, who first described it mathematically in the late 1800s, is the key to understanding why the sun appears yellow and why the sky is blue. It is the physical process that alters sunlight as it passes through air, selectively removing certain wavelengths and allowing others to pass through relatively unaffected. To understand Rayleigh scattering, we need to think about what happens when an electromagnetic wave encounters a molecule. The oscillating electric field of the light wave causes the electrons in the molecule to oscillate as well, vibrating back and forth at the same frequency as the light. These oscillating electrons then re-radiate light in all directions, like tiny antennas. This re-radiated light is what we mean by scattering. The molecule has taken light traveling in one direction and redirected some of it in other directions. The key insight from Rayleigh's work is that the intensity of this scattered light depends very strongly on wavelength. Specifically, for particles much smaller than the wavelength, the intensity of scattered light is inversely proportional to the fourth power of the wavelength. If one wavelength is twice as long as another, it will be scattered 16 times less strongly, because 2 to the fourth power is 16. This relationship has profound consequences for sunlight passing through air. Blue light, with its shorter wavelength, is scattered much more strongly than red light. Violet light is scattered even more strongly than blue. Green and yellow are intermediate. Red and orange, with the longest wavelengths in the visible spectrum, are scattered the least. This wavelength dependence is the fundamental reason why the sun's white light does not remain white as it travels through the atmosphere. The atmosphere preferentially removes blue light, scattering it out of the direct beam and into the sky. The light that continues forward to your eyes has less blue than it started with. With blue partially removed, the remaining light is richer in yellows and reds, and the sun appears yellowish rather than white. This is not a dramatic effect when the sun is high in the sky and its light passes through a moderate amount of atmosphere. The yellowing is subtle, a gentle warming of the color temperature rather than a stark change, but it is real and measurable. The sun at noon appears slightly yellower than it does from space. As the sun moves lower toward the horizon, the effect becomes much more pronounced, as we will explore in detail later. But even at noon, even on a clear day, the atmosphere is altering the sun's color. To fully understand this, we need to look more carefully at the scattering process itself, at the mathematics that Lord Rayleigh developed, and at what happens to sunlight as it travels through kilometers of air. Rayleigh scattering is named after John William Strutt, the third Baron Rayleigh, a British physicist who lived from 1842 to 1919. In 1871, Rayleigh published a paper analyzing how small particles scatter light, deriving a mathematical formula that described the intensity of scattered light as a function of particle size, wavelength, and scattering angle. This work was part of an effort to understand why the sky is blue, a question that had puzzled scientists for some time. The key insight was recognizing that air molecules are much smaller than the wavelengths of visible light. This means we cannot treat light scattering as simple reflection off a surface. Instead, we must think about how the oscillating electromagnetic field of the light wave interacts with the electrons in the molecule. Imagine a light wave traveling through air. The electric field component of this wave oscillates up and down, or side to side, depending on the polarization, many trillions of times per second. When this oscillating field encounters a molecule, it exerts forces on the electrons, which are negatively charged. The electrons respond by moving slightly back and forth in sync with the field oscillations. The molecules. Positive atomic nuclei are much heavier and barely move, but the light electrons are easily pushed around. These oscillating electrons then generate their own electromagnetic waves, radiating light in all directions. This radiated light has the same frequency as the original light wave, but it travels in many directions rather than just forward. This is the scattered light. The molecule acts like a tiny antenna, receiving the incoming light wave and broadcasting it in all directions. The strength of this scattering process depends on several factors. One is how strongly the molecule's electrons respond to the light's electric field, which is related to the molecule's polarizability. Larger molecules with more loosely bound electrons are generally more polarizable and scatter more strongly. But even more important is the wavelength of the light. Rayleigh showed mathematically that for particles much smaller than the wavelength, the intensity of scattered light is proportional to 1, divided by wavelength to the 4th power. This is often written as intensity being proportional to EL to the -4, where L is the Greek letter lambda, commonly used to denote wavelength. This 4th power dependence is extremely strong. Consider blue light at 470 nanometers wavelength and red light at 700 nanometers wavelength. The ratio of these wavelengths is 700 divided by 470, which is approximately 1.49. But when we take this to the 4th power, we get 5.06. Blue light is scattered more than 5 times as strongly as red light. If we compare violet light at 400 nanometers to red light at 700 nanometers, the wavelength ratio is 1.75, and the 4th power of this is 9.38. Violet light is scattered more than 9 times as strongly as red light. This dramatic wavelength dependence means that as white light from the sun passes through air, the different colors are affected very differently. Blue and violet light scatter strongly, while red and orange scatter weakly. The scattered blue light spreads throughout the sky, which is why the sky appears blue when we look at it away from the sun. The forward-traveling beam, meanwhile, becomes depleted in blue and enriched in red and orange. It is worth being precise about what we mean by scattering. When a photon of light encounters a molecule and scatters, it does not get absorbed and destroyed. The molecule does not gain energy, at least not in the Rayleigh scattering process, which is elastic scattering. Elastic means that the energy of the photon is conserved. A blue photon that scatters remains a blue photon with the same wavelength and energy. What changes is the direction of travel. Most scattering events redirect light at large angles, 90 degrees or more from the original direction. So, if sunlight is traveling downward through the atmosphere toward the ground, scattered light is sent off to the sides, upward, and in all other directions. Some of this scattered light travels downward and reaches our eyes, which is why the sky appears bright and blue rather than black, as it does in space where there is no air to scatter light. But much of the scattered light goes in other directions and never reaches us. The key point is that scattering removes light from the direct beam. Imagine a narrow beam of sunlight traveling straight down through the atmosphere. As it goes, some of the light scatters at each point where it encounters molecules. Blue light scatters more, red light scatters less, but both scatter to some degree. The further the light travels through air, the more gets scattered out of the beam. By the time the beam reaches the ground, it has been depleted of some of its original intensity, with blue wavelengths depleted more than red ones. This depletion is called attenuation. The atmosphere attenuates sunlight, reducing its intensity. The amount of attenuation depends on how much air the light passes through, which depends on the path length. When the sun is directly overhead, sunlight enters the atmosphere from above and travels straight down, passing through the minimum possible amount of air. The path length through the atmosphere in this case is called one air mass. When the sun is at an angle, say 30 degrees above the horizon, the path length is longer because the light enters the atmosphere at slant. The path length might be about 2 air masses. When the sun is very low on the horizon, the path can be 10 or 20 or even 40 air masses, depending on exactly how low the sun is. The closer to the horizon, the more air the light must pass through. For each air mass of path length, a certain fraction of each wavelength gets scattered out. Blue light loses a larger fraction than red light because of the fourth power wavelength dependence. As the path length increases, this effect multiplies. After passing through 10 air masses, blue light might be reduced to a tiny fraction of its original intensity, while red light is reduced much less. This is why the sun appears orange or red at sunset. The short wavelength colors have been almost entirely scattered away, leaving only the long wavelength colors to reach your eyes. But we are getting ahead of ourselves. We will explore sunsets in detail later. For now, let us focus on the situation when the sun is high in the sky, when the path length is relatively short, and the effect is more subtle. When the sun is overhead, sunlight travels through approximately 1 air mass of atmosphere. In this journey of perhaps 8 to 10 kilometers through air, some scattering occurs. Blue light is preferentially scattered, so the direct beam that reaches the ground has somewhat less blue than it started with. Red light is scattered less, so it remains closer to its original intensity. The net effect is that the light reaching the ground has a slightly different spectral composition than the light that entered the atmosphere. This can be measured precisely. Scientists have instruments called spectroradiometers that measure the intensity of light at each wavelength. When such an instrument measures sunlight at ground level on a clear day with the sun high in the sky, the spectrum shows a slight deficit in the blue compared to space-based measurements. The difference is not enormous. Blue light is not absent, just somewhat reduced. But it is enough to shift the color perception from white toward yellow. Our eyes are sensitive to this shift. The 3 types of cone cells in our retinas, which detect short, medium, and long wavelengths, each receive slightly different signals from ground-level sunlight compared to space-based sunlight. The short wavelength cones, most sensitive to blue, receive a slightly weaker signal. The medium and long wavelength cones, most sensitive to green and red, receive signals closer to their space-based values. Our brain interprets this combination as a slightly warmer, yellower light than pure white. The effect is subtle enough that we often do not consciously notice it. Our visual system is good at adapting to the color of illumination through color constancy. White objects still appear white under ground-level sunlight, even though the illumination is slightly yellowish. But if we could see the sun from space and from the ground side by side, the difference would be apparent. The space-based sun is cooler and whiter. The ground-based sun is warmer and yellower. This is Rayleigh scattering at work. It is an invisible but constant process, happening in the air around us all the time. Every molecule in the atmosphere is scattering sunlight, redirecting it, changing the distribution of colors. The cumulative effect of countless trillions of individual scattering events is to filter the sun's white light, shifting it toward yellow at noon and toward orange and red at sunrise and sunset. Understanding this process requires patience and careful thought. The mathematics can be complex, involving electromagnetic theory and quantum mechanics at a deeper level, but the basic principle is simple. Small particles scatter short wavelengths more strongly than long wavelengths. Air molecules are small compared to visible light wavelengths. Therefore, air scatters blue more than red. Therefore, sunlight passing through air loses blue preferentially. Therefore, the sun appears yellower than it truly is. This is not the only effect at work in the atmosphere. There are other forms of scattering, such as scattering from larger particles like dust and water droplets, which scatter all wavelengths more equally and give clouds their white appearance. There is absorption by certain gases, particularly ozone in the stratosphere, which absorbs strongly in the ultraviolet. There are many complications and subtleties, but Rayleigh scattering is the dominant effect for understanding why clear air alters sunlight's color. It is the reason the sky is blue. It is the reason the sun appears yellow rather than white. It is a simple physical process with profound consequences for our daily experience of light and color. Let us trace the path of a beam of sunlight as it travels from the sun to your eyes on a clear day at noon when the sun is high in the sky. This journey takes approximately 8 minutes and 20 seconds across the 150 million kilometers of space between the sun and Earth, traveling at the speed of light, 300,000 kilometers per second. For most of this journey, nothing happens. Space is a vacuum, devoid of matter, and light propagates through it unimpeded. The beam carries white light, a mixture of all visible wavelengths in the proportions that the sun's 5,778 Kelvin surface emits them. Red light at 700 nanometers, orange at 600, yellow at 580, green at 520, blue at 470, violet at 400. All present, all traveling together, all at the same speed. As the beam approaches Earth, it encounters the first wisps of the upper atmosphere 100 kilometers or more above the surface. At this altitude, the air is extraordinarily thin, less than 1/millionth the density of sea level air. The few atoms and molecules present begin to scatter some of the light, but the effect is negligible. The beam continues essentially unchanged. Descending lower, the atmosphere grows denser. At 80 kilometers altitude, we are in the mesosphere, where the air is still millions of times thinner than at sea level, but beginning to have measurable effects. Sunlight here causes chemical reactions, breaking apart molecules, ionizing atoms. Some ultraviolet light is absorbed by ozone molecules in the stratosphere below, but visible light continues through, essentially unaffected. By 50 kilometers altitude in the stratosphere, the air density has increased substantially, though it is still only about 1,000th of sea level density. Here, the ozone layer plays a crucial role, absorbing most of the sun's ultraviolet light and protecting life on the surface. But for visible light, the stratosphere is still largely transparent. Some scattering occurs, but the total amount of air is still relatively small. At 20 kilometers, we enter the troposphere, where the vast majority of the atmosphere's mass resides. The air density increases rapidly with every kilometer of descent. By 10 kilometers, typical cruising altitude for commercial aircraft, the pressure is about 1/4 of sea level. By 5 kilometers, it is about half. At sea level, it reaches its maximum. Throughout the troposphere, Rayleigh scattering continuously removes light from the direct beam. At each point in space, the nitrogen and oxygen molecules scatter some of the passing light. Blue light scatters strongly, sending photons off in random directions. Some head back up toward space, some travel horizontally. Some go downward toward the ground, but at angles that miss your location. All of these are effectively removed from the beam heading toward your eyes. Red light also scatters, but much less. For every 100 blue photons scattered, perhaps only 20 red photons scatter, the exact ratio depending on the wavelengths we compare. This means that as the beam descends, it loses blue photons faster than red photons. The beam gradually shifts in color from white toward yellow. The effect accumulates with distance traveled. Each kilometer of air removes a certain fraction of each wavelength. By the time the beam reaches the ground after passing through 8 to 10 kilometers of air, the blue content has been reduced noticeably. Not eliminated, but reduced enough to shift the color. We can calculate this effect. The fraction of light remaining after passing through a distance of air is given by an exponential decay function. The intensity at any given wavelength decreases as e raised to the power of negative optical depth, where optical depth measures how much scattering and absorption occurs.
For Rayleigh scattering, the optical depth is proportional to wavelength to the -4, the inverse fourth power that we have already discussed. At sea level, with the sun directly overhead, the optical depth for blue light at 470 nanometers is approximately 0.2. This means that the intensity of blue light is reduced by a factor of e to the -0.2, which is about 0.82 or 82%. 18% of the blue light has been scattered out of the beam. For red light at 700 nanometers, the optical depth is much smaller, approximately 0.04. The intensity is reduced to e to the -0.04, which is
0.96 or 96%. Only 4% has been scattered. This means that red light passes through the atmosphere with 96% of its intensity intact, while blue light arrives with only 82%. The ratio of blue to red has changed. In space, before entering the atmosphere, suppose the ratio of blue intensity to red intensity was 1.0. After passing through the atmosphere, the ratio is now 0.82 divided by 0.96, which is approximately 0.85. There is less blue relative to red. This sounds like a small change, and numerically it is, but human color perception is sensitive to such differences. When our cone cells receive light with a ratio of blue to red of 0.85 rather than 1.0, the signal our brain receives is different. The color shifts from neutral white toward warm yellow. The effect is subtle at noon. The sun still appears fairly white, perhaps with a slight golden tint. On a very clear day at high altitude, with the sun perfectly overhead, the color may be almost indistinguishable from white, but it is always slightly yellower than it would appear from space. The atmosphere always affects the color, even when the effect is minimal. As the sun moves away from the zenith, even at noon in the summer at mid-latitudes, the path length increases slightly. Instead of traveling straight down through one air mass, the light travels through perhaps 1.1 or 1.2 air masses. The optical depth increases proportionally, and the color shift becomes slightly more pronounced. The sun looks a bit more yellow, a bit warmer. All of this is happening invisibly, automatically, every moment. You look up at the sun, or more likely you see sunlight streaming through a window or illuminating objects around you, and you perceive a certain color. That color is the result of white light from the sun being filtered by 8 to 10 kilometers of air. The filtering removes blue preferentially, and what remains appears yellow. The scattered blue light, meanwhile, does not disappear. It spreads throughout the sky, bouncing between molecules, eventually reaching the ground from all directions. When you look at the sky away from the sun, you see this scattered blue light. That is why the sky is blue. The blue that is missing from the direct sunlight has been redirected throughout the atmosphere. This is a beautiful symmetry. The sun appears yellower than it should because the atmosphere removes blue light. The sky appears blue because that removed light scatters everywhere. The two phenomena are two sides of the same coin, both consequences of Rayleigh scattering. On a clear day at noon, the effect is relatively subtle, but wait for the sun to approach the horizon at sunset or sunrise, and the effect becomes dramatic. The path length increases tenfold or more, the blue light is almost entirely removed, and the sun glows orange or red. To understand this more extreme case requires examining what happens when sunlight must travel through much more atmosphere than at noon. When the sun sits low on the horizon, either at dawn or dusk, its light must travel through far more atmosphere to reach you than at noon. The difference is dramatic. Instead of passing through 8 to 10 kilometers of air in a nearly vertical path, the light now travels horizontally through the atmosphere for hundreds of kilometers before descending to your location. The path length can easily be 10 times longer than at noon, or even 40 times longer when the sun is just barely above the horizon. This extended path length amplifies every effect we discussed earlier. Rayleigh scattering, which removes 18% of blue light when the sun is overhead, now removes nearly all of it after the light passes through 10 or 20 or 40 air masses. What little blue light remains is too weak to affect the sun's perceived color significantly. Instead, the color is dominated by the long wavelength light that scatters less and therefore survives the journey. Let us be specific about the numbers. Recall that at 1 air mass, the optical depth for blue light at 470 nanometers is approximately 0.2. At 10 air masses, the optical depth is 10 times larger, approximately 2.0. The fraction of blue light remaining is e to the negative 2, which equals approximately 0.14 or 14%. 86% has been scattered away. At 20 air masses, the optical depth for blue is 4.0, and the remaining intensity is e to the negative 4, approximately 0.02 or 2%. 98% of the blue light has been scattered. For red light at 700 nanometers, the situation is very different. At 1 air mass, the optical depth is 0.04. At 10 air masses, it is 0.4. The remaining intensity is e to the negative 0.4, approximately 0.67 or 67%. Only 33% has been scattered. At 20 air masses, the optical depth for red is 0.8, and the remaining intensity is e to the negative 0.8, approximately 0.45 or 45%. Even after this extended path, nearly half the red light remains. The contrast is stark. At 20 air masses, 2% of blue light remains, but 45% of red light remains. The ratio of blue to red has dropped from 1.0 in space to approximately 0.04. Blue is now negligible compared to red. The light is no longer white or even yellow. It is orange or red. This is why sunsets are red. The color we see when we look at the setting sun is the color of sunlight after nearly all short wavelength light has been removed by Rayleigh scattering. Only the long wavelengths, red and orange, penetrate. The long atmospheric path. When these colors reach our eyes without significant blue or green to balance them, we see the sun as red. The exact color depends on several factors. One is the precise path length, which depends on the sun's angle above the horizon. When the sun is right at the horizon, the path is longest and the color most extreme, often a deep red. As the sun rises or sets, passing through angles slightly above the horizon, the path shortens and the color shifts from deep red to orange to yellow. Another factor is atmospheric conditions. Clean, dry air produces the most vivid reds because Rayleigh scattering dominates and the wavelength dependence is strongest. If the air contains dust, smoke, or water droplets, these larger particles scatter all wavelengths more equally through Mie scattering, which does not have the strong wavelength dependence of Rayleigh scattering. This can produce paler colors, sometimes white or gray near the sun with color only at the edges. Volcanic eruptions can create spectacular sunsets by injecting fine particles into the stratosphere. These particles are small enough to scatter blue light strongly, but large enough to scatter red light more than molecules alone would. The result is often intensely colored sunsets with deep oranges and purples that can persist for years after a major eruption as the particles slowly settle out of the stratosphere. Water vapor also plays a role. Humid air contains more molecules per unit volume and can increase scattering slightly. More importantly, humidity often accompanies clouds, and clouds can reflect and scatter sunlight in complex ways, creating varied and dramatic sunset colors. But the fundamental reason sunsets are red remains Rayleigh scattering and the long atmospheric path. Even on the clearest, driest day, the setting sun will appear orange or red simply because blue and green light cannot survive the journey through 40 air masses of perfectly clean air. The same physics applies at sunrise. The path length through the atmosphere is just as long when the sun rises as when it sets. The colors are similar, though sunrise and sunset can look different in practice due to different atmospheric conditions. Evening air often contains more dust and particles stirred up by daytime winds, while morning air may be cleaner and calmer. Evening air is typically warmer, having been heated all day, while morning air is cooler. These factors can affect clouds and humidity, which in turn affect the appearance of the sky. But the underlying color physics is identical. Red sunrises and red sunsets both result from the long path through atmosphere removing short wavelength light. Between the extremes of noon and sunset lie all the intermediate times of day. As morning progresses and the sun rises higher, the path length decreases continuously. At 30 degrees above the horizon, the path is about 2 air masses. At 45 degrees, about 1.4 air masses. Each change in angle corresponds to a change in path length and therefore a change in how much of each wavelength survives to reach the ground. This means the sun's apparent color changes throughout the day. It is most yellow at noon when the path is shortest, though even then it is yellower than the true white. It becomes progressively more orange and red as it approaches the horizon. If you could watch carefully with a calibrated color sensor, you would see the color shift continuously and predictably based on the sun's angle. Most of us do not notice the gradual shift during the day because our visual system adapts. The color of illumination is something our brain tends to factor out, focusing instead on the relative colors of objects in the scene. But the shift is real and measurable. Photographers are well aware of it. The warm golden light of late afternoon, often called the golden hour, is sunlight that has traveled through several air masses, losing blue and taking on yellow and orange tones. This light is favored for portraits and landscapes because it is flattering and creates a warm atmosphere. It is sunlight partially filtered by the atmosphere, not yet as extreme as sunset, but distinctly different from the cooler light of midday. All of this, the changing color of the sun throughout the day, the blue sky overhead, the red sunsets and sunrises, all of it is Rayleigh scattering at work. It is a single physical phenomenon manifesting in many visible ways, all because molecules are small, wavelength matters, and short wavelengths scatter more than long ones. We have discussed at length how the atmosphere alters sunlight, removing blue wavelengths and allowing yellow and red to dominate. But ultimately, color is not just a property of light. It is also a product of perception, of how our eyes and brain interpret the light that enters them. To fully understand why we see the sun as yellow, we must understand how human color vision works. Color vision begins in the retina, the light-sensitive layer at the back of the eye. The retina contains two main types of photoreceptor cells, rods and cones. Rods are extremely sensitive to light and work well in dim conditions, but they do not distinguish colors. They all contain the same light-sensitive pigment and respond similarly to all visible wavelengths. In very low light, when only rods are active, we see in shades of gray. Cones are less sensitive than rods and require brighter light to function, but they enable color vision. There are three types of cones, each containing a different light-sensitive pigment that responds most strongly to different wavelengths. These are commonly called S, M, and L cones for short, medium, and long wavelength sensitivity. S cones, also called blue cones, contain a pigment that absorbs most strongly around 420 nanometers in the blue-violet part of the spectrum. These cones respond best to short wavelength light and send signals to the brain when blue light enters the eye. M cones, also called green cones, contain a pigment that peaks around 530 nanometers in the green part of the spectrum. They respond to medium wavelengths. L cones, also called red cones, contain a pigment that peaks around 560 nanometers, which is actually in the yellow-green part of the spectrum, not red. Despite being called red cones, they respond most strongly to yellow-green light. However, they extend their sensitivity into the red more than the M cones do, so they are relatively more sensitive to red light. The exact peak wavelengths vary slightly between individuals, and the response curves of the cones are broad, overlapping substantially. S cones respond to wavelengths from about 400 to 500 nanometers. M cones respond from about 450 to 650 nanometers. L cones respond from about 500 to 700 nanometers. The overlap is significant, meaning any given wavelength activates multiple cone types to different degrees. Color perception arises from comparing the responses of the three cone types. When light enters the eye, each wavelength activates each cone type to some degree based on that cone's sensitivity curve. The brain receives three numbers, representing the total response of S, M, and L cones. From these three numbers, it constructs our experience of color. Pure red light at 700 nanometers activates L cones strongly, M cones weakly, and S cones not at all. The brain interprets this pattern, strong L with weak M and no S, as the color red. Pure blue light at 470 nanometers activates S cones strongly, M cones moderately, and L cones weakly. Strong S with moderate M and weak L is interpreted as blue. Pure green light at 520 nanometers activates M cones strongly and L cones moderately, with S cones responding weakly. Strong M with moderate L and weak S is green. For yellow light at 580 nanometers, both M and L cones respond strongly and S cones respond weakly. This combination, strong M and L with weak S, is perceived as yellow. White light, containing all wavelengths in equal amounts, activates all three cone types roughly equally. When S, M, and L all send similar signals, the brain interprets this as white or gray, depending on overall intensity. Now consider what happens when sunlight, altered by the atmosphere, enters the eye. The light is no longer balanced across all wavelengths. Blue has been partially removed by Rayleigh scattering. Red and orange are closer to their original intensities. Green and yellow are intermediate. When this light hits the retina, S cones receive less stimulation than they would from true white light, because blue wavelengths are depleted. M and L cones receive stimulation closer to what they would get from white light, because longer wavelengths are less affected. The pattern of signals sent to the brain is somewhat reduced S, with relatively normal M and L. The brain interprets this pattern as a color that is less blue than white, which means warmer, more yellow or orange. At noon, the effect is subtle, a slight shift toward yellow. At sunset, with blue almost entirely absent, the shift is dramatic, producing orange or red. This is how atmospheric filtering translates into color perception. The atmosphere changes the physical spectrum of light. The changed spectrum activates cone cells differently than white light would. The brain interprets the different pattern of activation as a different color. It is worth noting that color perception is not entirely determined by the physical spectrum. The brain performs sophisticated processing using context and expectation to influence what colors we perceive. This is called color constancy. A white piece of paper appears white whether we view it in sunlight, in shade, or under artificial lighting, even though the actual spectrum of light reflecting from the paper is quite different in each case. The brain recognizes that the paper is white and adjusts perception accordingly, factoring out the color of the illumination. This means that our perception of the sun's color can be influenced by expectation and context. If we expect the sun to be yellow, we may perceive it as more yellow than a purely objective measurement would suggest. Our visual system is not a passive light meter, but an active interpreter of scenes. Nevertheless, the physical changes to the spectrum are real and measurable. Instruments confirm that ground-level sunlight is depleted in blue compared to space-based sunlight. Our cone cells genuinely receive different signals. The yellow appearance of the sun is not purely subjective or illusory. It reflects a real change in the light caused by the atmosphere. Different animals have different color vision systems and would perceive the sun differently. Many birds have 4 types of cones, including one sensitive to ultraviolet light. They can see colors we cannot imagine. To a bird, the sun might appear quite different, especially because the atmosphere scatters ultraviolet light even more strongly than blue, following the same inverse fourth power law. A bird's ultraviolet sensitive cones would receive very little signal from ground-level sunlight, while their other cones would respond similarly to ours. Many mammals, including dogs and cats, have only 2 types of cones and are essentially red-green colorblind. They can distinguish blue from yellow, but cannot distinguish red from green. To them, the sun's shift from white to yellow might be less noticeable, though the shift from yellow to red at sunset would still be apparent. Some animals, particularly nocturnal ones, have mostly rods and very few cones. They see little or no color. To them, the sun is simply bright, not colored in any meaningful way. Humans, with our 3 cone types, occupy a middle ground. We have reasonably good color vision, able to distinguish many hues, though not as many as birds. Our color perception is well suited to our environment and has likely been shaped by evolution to be useful for tasks like finding ripe fruit, identifying plants, and reading facial expressions. The specific response curves of our cones, peaking where they do, make us sensitive to the kinds of color changes that Rayleigh scattering produces. We can easily distinguish the white sun of space from the yellow sun of Earth, the yellow sun of noon from the orange sun of late afternoon. These distinctions are built into our visual system. It is also worth noting that color perception can vary between individuals. Some people have genetic variations that affect their cone pigments, leading to slightly different color vision. The most common form of color blindness, red-green color blindness, results from having 2 very similar cone types where most people have distinct M and L cones. People with this condition cannot distinguish certain shades of red and green, but can still see blue and yellow normally. Rarer conditions involve missing one cone type entirely or having unusual cone pigments. Each of these variations changes how colors are perceived. So while we can speak generally about how humans see the sun's color, there is individual variation. Not everyone experiences color identically. Despite this variation, the general pattern holds. For people with typical trichromatic color vision, ground-level sunlight appears yellower than space-based sunlight because the atmosphere removes blue, and our visual system interprets light with reduced blue as warmer in color. This is a consequence of atmospheric physics combined with the biology of human vision. Understanding why the sun appears yellow on Earth takes on additional meaning when we consider the broader context of stars, planets, and atmospheres throughout the universe. Earth's atmosphere is not unique in altering the appearance of its star. Any planet with an atmosphere will affect the light from its sun in ways that depend on the atmosphere's composition, density, and the wavelengths of light involved. The sun itself, as we have established, is a fairly typical star. Its spectral class is G2V, which places it among the yellow dwarf stars, though this classification is somewhat misleading given that the sun is actually white. The classification system was developed based on how stars appear from Earth through our atmosphere, so a G-type star is one that appears yellowish from the ground. From space, G-type stars appear white. Stars come in many different temperatures, and this determines their true colors as blackbody radiators. The hottest stars, with surface temperatures above 30,000 Kelvin, are class O stars. These emit strongly in the ultraviolet and appear blue-white or blue. They are rare and massive, burning their fuel quickly and living only a few million years. Cooler than O stars are B stars, around 20,000 Kelvin, still blue-white. Then come A stars around 10,000 Kelvin, appearing white. F stars are around 7,000 Kelvin and appear white with perhaps a slight yellow tint. G stars like the Sun are around 5,500 to 6,000 Kelvin and appear white, though they seem yellow from Earth's surface. Cooler still are K stars around 4,500 Kelvin, which genuinely are orange in color. M stars, the coolest and most common, are around 3,000 Kelvin and appear red. These red dwarfs make up about 70% of all stars in the galaxy, but are too dim to see with the naked eye from Earth, except for the very nearest ones. If Earth orbited an M star instead of the Sun, the daytime sky would be quite different. The star's light would be genuinely red, rich in long wavelengths and poor in short ones. A Rayleigh scattering would still occur, removing blue more than red, but there would be little blue to remove in the first place. The sky might appear darker, less brightly illuminated, with the star itself appearing deep red. Plants on such a world, if they existed, might evolve different pigments for photosynthesis. Earthly plants use chlorophyll, which absorbs blue and red light and reflects green, making plants appear green. Under a red star, plants might use pigments that absorb red and infrared more efficiently, possibly appearing black or dark purple to reflect as little of the available light as possible. If Earth orbited an A or F star, hotter and brighter than the Sun, the star would appear very white or slightly bluish. These stars emit more blue and ultraviolet light than the Sun does. The atmosphere would still scatter blue, preferentially, so the sky would be blue, but the star itself would be cooler in color temperature, appearing less yellow than our Sun does from Earth. Other planets in our own solar system have atmospheres that affect light differently. Mars has a very thin atmosphere, mostly carbon dioxide, with only about 1% of Earth's surface pressure. The atmospheric path length for sunlight on Mars is much shorter in terms of molecular density. Rayleigh scattering still occurs, but the effect is much weaker. The Sun appears closer to white on Mars than on Earth. Interestingly, the Martian sky appears butterscotch or pinkish tan during the day, not blue, because of dust suspended in the air. This dust consists of particles much larger than molecules, so my scattering dominates over Rayleigh scattering. The dust scatters red light more than Earth's atmosphere does, giving the sky its unusual color. Venus has an extraordinarily thick atmosphere with surface pressure 92 times greater than Earth's. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. Sunlight must pass through enormous amounts of gas and cloud to reach the surface. The light that arrives is dim and diffuse, filtered through kilometers of dense atmosphere. The color would be affected dramatically, though no human has stood on Venus's surface to observe it directly. Spacecraft that have landed there send back images showing a dim, orange light, though these images are affected by the camera's properties and are not necessarily representative of what a human eye would see. Jupiter, Saturn, Uranus, and Neptune have no solid surfaces, being gas giants or ice giants. Their atmospheres are many thousands of kilometers thick. Light from the Sun entering these atmospheres undergoes complex scattering and absorption by various gases and cloud layers. The colors we see when we observe these planets, the bands and zones and spots, are the colors of their atmospheres as lit by sunlight. The Sun itself, as seen from deep within these atmospheres, would appear heavily filtered and altered in color, if visible at all. Saturn's moon Titan has a thick atmosphere of nitrogen and methane, with surface pressure 1.5 times Earth's. The methane in the upper atmosphere absorbs red light strongly, so sunlight reaching Titan's surface is orange and dim. The sky, as seen by the Huygens probe which landed on Titan in 2005, appears orange. The Sun would appear dimmed and perhaps yellowish-orange due to the loss of blue and red wavelengths. Exoplanets, planets orbiting other stars, likely have enormous diversity in atmospheres. Some may have no atmosphere at all. Some may have atmospheres denser than Venus's. Some may have atmospheres with compositions unlike anything in our solar system, perhaps rich in gases like hydrogen sulfide, ammonia, or exotic compounds we have never encountered. Each of these atmospheres would alter the appearance of its star in unique ways. The star's true color, determined by its temperature, would be filtered by the atmosphere's particular scattering and absorption properties. An alien standing on an exoplanet would see their star in a E color determined by the interplay of the star's spectrum and their atmosphere's physics. This has implications for the search for life beyond Earth. When astronomers analyze the light from exoplanets, looking for biosignatures or signs of habitability, they must account for atmospheric effects. The spectrum of light reflected from a planet includes both the star's light and modifications introduced by the planet's atmosphere. By carefully analyzing these modifications, scientists can infer the atmosphere's composition, temperature, and even potentially detect the presence of gases like oxygen that might indicate life. In a sense, every time we look at the yellow sun in Earth's blue sky, we are seeing the signature of our atmosphere written in color. We are seeing Rayleigh scattering in action, the physical process that reveals Earth has an atmosphere made of small molecules. If Earth had no atmosphere, the sun would appear white and the sky would be black, like the moon's sky. The colors we see are evidence of air, evidence that we live at the bottom of an ocean of nitrogen and oxygen that shields us, warms us, and enables us to breathe. This perspective connects the simple observation of the sun's color to deep questions about planets, atmospheres, and the conditions necessary for life. The yellow sun is not just an aesthetic fact. It is a reminder that we live on a planet with an atmosphere, that light interacts with matter in predictable ways, that physics is universal. The same processes that make our sun appear yellow would make stars appear different colors on other worlds with other atmospheres. Understanding one helps us understand all the others. Historically, it took humanity a long time to understand these connections. Ancient peoples knew the sun and sky intimately, but did not understand why they had the colors they did. The sky's blue was a mystery. The sunset's red was beautiful but unexplained. In the 1500s and 1600s, scientists began to understand light better. Newton's prism experiment showed that white light contains all colors. Later work developed the wave theory of light, showing that light is an electromagnetic wave with wavelength and frequency. In the 1800s, as physics advanced, scientists began to wonder why the sky is blue. Several theories were proposed. John Tyndall, an Irish physicist, showed experimentally in the 1860s that tiny particles could scatter blue light more than red light, demonstrating the principle, though not fully explaining it mathematically. Lord Rayleigh, in 1871, provided the mathematical framework, deriving the inverse fourth power, wavelength dependence for scattering by particles much smaller than the wavelength. This explained quantitatively why air molecules scatter blue light so much more effectively than red light. The understanding was refined further in the early 1900s as quantum mechanics developed and the detailed mechanisms of light-matter interaction became clearer. By the mid-20th century, with the advent of space exploration and the ability to measure the sun's spectrum from above the atmosphere, the white nature of the sun was confirmed directly. Now, in the 21st century, this knowledge is standard in physics and astronomy textbooks. We understand the sun's color, the sky's color, and the reasons for both. We can calculate expected colors for stars of any temperature and atmospheres of any composition. We can even speculate about what the sky might look like on distant exoplanets, based on models of their atmospheres and their stars' spectra. This progression from observation to understanding is science at work. It takes what seems like a simple fact, the sun is yellow, and reveals that it is not simple at all. The sun is white. The atmosphere makes it appear yellow. This realization opens up a deeper understanding of light, matter, temperature, molecules, scattering, and how all of these connect. Every time you see the sun, you are witnessing this physics in action. The light has traveled 93 million miles through space, then 8 miles through air, scattering and filtering along the way. What reaches your eyes is the product of nuclear fusion in the sun's core, black body radiation from its surface, the inverse fourth power law of Rayleigh scattering, and the biological machinery of your retina and brain. All of this comes together to create the simple, immediate experience of seeing a yellow sun in a blue sky. We have traveled through a landscape of light and atmosphere, wavelengths and molecules, vision and perception. We began with a simple question. Why does the sun appear yellow when it is actually white? The answer, as we have seen, is not simple at all. It requires understanding physics, astronomy, chemistry, biology. It requires tracing the path of sunlight from its origin to our eyes, seeing how each stage of the journey alters what we ultimately perceive. The sun is white. This is a measured fact, confirmed by instruments in space, by the mathematics of blackbody radiation, by the spectrum emitted from a 5,778 Kelvin surface. The sun emits all colors of visible light in balanced proportions that combine to produce white. Earth's atmosphere, that thin shell of nitrogen and oxygen surrounding our planet, alters this white light as it passes through. Molecules in the air scatter light, and they scatter short wavelengths much more strongly than long wavelengths. Blue light scatters, red light passes through. By the time sunlight reaches the ground, some of the blue has been removed and the remaining light appears yellower than it started. This is Rayleigh scattering, named after the physicist who first described it mathematically. It is a consequence of the size of molecules being much smaller than the wavelength of light and the electromagnetic interactions that result from this size difference. The effect follows an inverse fourth power law, meaning wavelength matters enormously. Small changes in wavelength produce large changes in scattering efficiency. At noon, with the sun high in the sky, the effect is subtle. The sun appears slightly yellow, warmer than pure white. As the sun approaches the horizon, the effect becomes dramatic. The path length through atmosphere increases tenfold or more, and nearly all the blue light is scattered away, leaving only orange and red to reach our eyes. This is why sunsets and sunrises are red. Our eyes and brain interpret these changes in spectral composition as changes in color. The three types of cone cells in our retinas respond differently to light of different wavelengths. When blue is depleted, the pattern of signals sent to the brain changes, and we perceive a warmer color. At noon, yellow; at sunset, orange or red. This phenomenon is not unique to Earth. Any planet with an atmosphere will alter its star's light in ways determined by the atmosphere's properties. Different atmospheres would produce different colors. The yellow sun and blue sky that we see are specific to Earth's particular mix of nitrogen and oxygen at our particular atmospheric pressure and density. Understanding this connects us to the broader universe. The same physics that makes our sun appear yellow operates on every planet with an atmosphere around every star. The same principles of light, scattering, temperature, and wavelength apply throughout the cosmos. By understanding one star and one atmosphere deeply, we gain insight into countless others. There is something quietly profound in knowing that the familiar yellow sun is not truly yellow, that the color we see is created by the air around us, that light and matter interact in ways both invisible and constant. Every moment, trillions upon trillions of scattering events are occurring in the atmosphere, each one redirecting a photon of light according to the laws of physics. The cumulative effect of these countless interactions is the world of color that we inhabit. The next time you see the sun, whether at noon or setting behind distant trees or rising over the ocean, you can know what you are really seeing. You are seeing white light that has been filtered by 8 miles of air. You are seeing the consequence of molecular scattering. You are seeing physics made visible. The sun has always been white since it formed 4.5 billion years ago from a collapsing cloud of gas and dust. Its color has never changed. What has changed is our understanding. We now know what earlier generations could only guess at. We know why the sky is blue and the sun is yellow. We know the mechanisms and the mathematics. We have measured and confirmed and understood. This knowledge does not diminish the beauty of a sunset or the warmth of sunlight on a summer afternoon. If anything, it enhances it. Knowing that the red light of sunset has traveled through 40 air masses, that nearly all its blue companions have been scattered into the sky, that what remains is the portion of the spectrum most resistant to scattering. This knowledge adds layers of meaning to the simple act of watching the sun go down. The universe operates according to physical laws, predictable and consistent. Light behaves as it must, scattering according to wavelength, absorbed and emitted by atoms following quantum mechanics. Yet within these laws, there is endless variety and beauty. The particular combination of a G-type star at Earth's distance and an atmosphere of nitrogen and oxygen produces the specific experience of a yellow sun in a blue sky. On another world with a different star and a different atmosphere, the experience would be different but equally determined by physics. We are fortunate to live in a time when these things can be known, when we have the tools and understanding to measure starlight and calculate scattering and explain the colors of the sky. Earlier generations could only wonder. Now we can know. The yellow sun, it turns out, is white. The atmosphere makes it yellow. And understanding why is a journey through some of the most beautiful physics in nature. The light continues, day after day, traveling from sun to atmosphere to eye, creating the familiar world of color that surrounds us. It will continue long after we are gone, unchanged by our understanding or lack of it. But for those who take the time to understand, there is a deeper appreciation available, a recognition that the simple question of the sun's color opens into profound truths about light and matter and the nature of perception itself. Thank you for spending this time exploring the mystery of the sun's white light and the yellow appearance we see from Earth. If you found this journey through light, atmosphere, and physics calming and enlightening, I invite you to like this video and subscribe to Nebula Nights for more deep explorations of cosmic phenomena. Each video is designed to be a peaceful, detailed examination of the universe around us, perfect for learning, relaxation, or gentle accompaniment to sleep. There are countless more questions to explore, countless more phenomena to understand. The universe is vast and full of quiet wonders waiting to be examined patiently and thoroughly. Subscribe to continue these explorations together. Until next time, may your days be illuminated by understanding and your nights filled with peaceful wonder.